All right, well, it's 7 o'clock, so let's begin. I want to welcome everybody to this joint meeting of the Washington, D.C. Quantum Computing Meetup and the Brooklyn Quantum Meetup. Today, we'll be hearing from Professor Himanshu Thapliyal on the topic of arithmetic circuits for quantum computing. But first, a little background. The Washington, D.C. Quantum Computing Meetup is a group for anyone interested in quantum computing and quantum information in the Washington, D.C. area and beyond. And there's a wonderful source of lectures by diverse researchers on their topics of interest. They generously partner with quantum meetups around the world. And I want to thank in particular Helen Ma for her help organizing this meeting, as well as Deb Goshal. My name is Matthew Weiss. I'm a writer and computer programmer, and I run the Brooklyn Quantum Meetup, which focuses on the intersection between physics, computation, and philosophy. You can find information about many of the topics we've discussed at heyredhat.github.io. And I invite you all to our next meeting this coming Saturday at 2 p.m., where we'll continue exploring the cubist formulation of quantum theory. That's cubism with a Q. I'm joined by my fellow moderator, Anna. Anna, take it away.
Hello, everyone. I'm Anna Gorgeva. My internet connection might be unstable. Very sorry about that. I'm a student at UC Berkeley studying data science and legal studies. I focus a lot on society, technology, and how data science and like our datafied world all interacts together through the perspective of ethical impact and justice. So today we'll be hearing from Dr. Himanshu Thapliyal, who is a professor of electrical engineering and computing at the University of Kentucky. He's also the co-director of the cybersecurity certification program there. Professor Thapliyal recently received the Mid-Career Achievement Award from IEEE, so congratulations on that. And he's also received on cybersecurity and technology. He is an editor of the Springer Nature Computer Science, IEEE Consumer Electronics Magazine, IEEE IoT Journal, and the editorial board member of Microelectronics Journal. Overall, he's leading the way in quantum computing and emerging technologies and emerging trends in sensors, IoT, and smart systems. So today he'll be discussing his work on arithmetic circuits for quantum computing. Thank you, Dr. Thapliyal, for being here today.
So quantum circuits for arithmetical operations are vital in designing quantum hardware for Shor's factoring algorithm, solving discrete log problems, quantum cryptanalysis, securing cryptosystems, circuit design for quantum algorithms. Quantum arithmetic circuits are widely used in quantum algorithms for quantum image orientation, pattern recognition, template matching. The quantum arithmetic circuits are vital to designing circuits for for scientific computing and quantum algorithms such as the Poisson equation, linear systems of equations, quantum rejection sampling. His talk will discuss quantum circuits for arithmetic functions with multimetric constraints and quantum circuits for basic image processing based on those proposed arithmetic circuits. After Dr. Thapliyal's talk, there will be a discussion period, question and answer. You may ask your questions directly or in the chat to be read aloud by Anna or myself. Thank you all for coming, and thank you, Dr. Thapliyal. We're excited to hear your lecture.
Myself, thank you. And so you can see my screen, right?
Yes.
Okay, great. So first of all, let me thank you to the organizers like Helen, Deb, Matthew, Anna, and other people for inviting me for this event. It was great to be here. And so today I will talk about arithmetic circuits for quantum computing. So this is some of the information if you need to contact me actually. So let me start. Okay, so let's talk about first about, I think I try to go from the basics perspective, and then we'll talk about some of the advanced stuff. And so that all of the people attending the talks comes to the same pace. So let's talk about the progress on the quantum computing hardware. So you might have seen that over a period of time, various companies such as IBM, Intel, Google, Microsoft, and several other companies, Honeywell, and all those companies are exploring the domains of the quantum computing. And you can see that, especially from the circuit design models, the quantum computing is seeing some growth in the number of qubits. And over a period of time, you can say that you can expect to have like around 1000 qubits by 2023. That's what the IBM is saying. And you might have seen the news that Google is expecting that by the end of 2019, 2029, they're expecting a practical quantum computer could be possible. So what is more important to us is that you can say that this field is getting huge momentum from the various industries, as can be evident by this particular slide. Now, there could be some performance gains that could be obtained by the use of some of these quantum algorithms. You might have heard about that. Many of these encryption algorithms could be vulnerable once the quantum computing systems are being available to us. And that's why you might have seen that people are already started exploring the domain of post-quantum cryptographic algorithms, and the underlying idea that those quantum algorithms or those post-quantum cryptographic algorithms will be resistant against these quantum attacks, right? So another interesting thing is that you can also see some beyond cryptanalysis, you can see some of the super polynomial improvement in scientific computing domains. And you can say they have some of the applications are people are exploring in the quantum chemistry, nuclear physics, and material science. Several other interesting areas are being explored in the finance side and all those things. And what you will see, what I want to talk to you today, that many of these algorithms will have some building blocks inside them. And one of the building blocks that is of very much importance is the quantum arithmetic circuits. However, you can see if you look into the classical computing domain, and you see that the arithmetic and the logic units forms the core component of your system. And whenever you need to perform some computations, you need to call some routines such as multipliers, division, all those things, right? So that's what we are talking about here, this quantum circuit for arithmetic functions. So you can say that over a period of time, this quantum circuit for cryptanalysis has also gained attention. There were several interesting groups, including ours, which were exploring these problems to develop some circuit which are efficient, resource efficient in nature. Now, I will, as I told you, we will talk about some of the fundamentals ideas, so that the talk is comprehensible to most of the people here. So most of the underlying idea is that the quantum computing is inherently reversible. And so the underlying idea is that there will be a one-to-one mapping between the inputs and the outputs. And so let's think in this case how, and then you will understand that why it is slightly difficult to tailor your circuits from the classical computing to the quantum computing, right? So one of the interesting example that you can think in this case, this is an XOR gate here, and which all of you can see here. And this XOR gate, which is a classical XOR gate, can have like, if you see, this is the truth table, right? For example, A, B, let me enable my pointer. Okay. So if you can see here, this is this A, B, when the inputs are 0, the output is also 0. When the inputs are 1, 1, the outputs are also 0. So now the interesting idea is that if you measure your output and you find out your output was 0, then your input could have been come from 0, 0, or your input could have been come from 1, 1, right? So that's why this gate is irreversible in nature, because it is difficult for somebody to measure the output as 0 and identify whether it was 0, 0 or 1, 1. So you inherently lose some information here. And so another interesting thing that people have over a period of time explored the reversibility into property. And the thing is that if you add an extra, you can say an output here, P equal to A, then if you see the truth table has changed now, and the truth table has become more like a reversible truth table, because for each input combination, you have a unique output combination. For example, if it is 0, 0, then your output is 0, 0. If it is 0, 1, it is 0, 1. And let's say in this case, if it is 0, 0, it is 0, it is 1, 1, and 0. But since we add one more, in this case, it is 1, 1. So output has become 1, 1, 0. So you can say it is a unique combination of the inputs and the outputs. Now, what do you observe now? The observability, you can see that in order to convert a circuit from an irreversible to a reversible circuit, you are trying to make sure that the number of input to the outputs are same. And you see that that is overhead in that way, because you need to convert your circuit in the reversible sense. Okay. So this is, as I told you, the truth tables and all those things. And then there are some other interesting reversible gates people have explored over a period of time. And this is one of the example of the CCC NOT gate. And in other words, people also call it sometimes the Toffoli gate, right? So if you look into the truth table, again, as I discussed with you, there are 3 inputs and the 3 outputs, and there is a 1-to-1 mapping between the inputs and the outputs, right? That's why these gates are inherently reversible in nature. So, so now the quantum, as I told you, several algorithms has been explored. People are also exploring the application of this quantum computing in image processing. And you will see that many of these quantum image processing operations require a lot of arithmetic function. And hopefully, if we have time today, we will see some examples of one of the application of the quantum image processing algorithms where the arithmetic circuits can play a critical role. So now, another thing that we have to talk about is that, so if you think in this case, the quantum world right now can be, you can say, split into 2 domains. One of them you can say is a noisy world. Right now, people call it NISQ quantum machines right now, which is like, which doesn't have the error correcting code. So that, so you can say there are the noisy qubits right now available. And the other could be like, say example, when you have a lot of qubits available, and let's say then you can even run the error correcting codes on the top of that, right? So to fix any of these errors. So some of the work that I will talk about is looking into those areas when we'll assume that you have sufficient qubits and you can run the error correcting codes on the top of that. So when you look into those particular things, you will see that there is a particular gate set that people try to optimize your circuit. So if you look at from, let's say from the classical sense, if you think in this case, let's say when somebody give you a technology file and they give you a set of functions such as XOR, NAND, NOR, and like that, and they say to you that, oh, you know what, you build your circuit only from this gate that are available to you, right? So that is the library that is being available to you. Similarly, when you're talking about these quantum systems, you have a set of gates that are available to you, and what people are saying that can you optimize some set of these gates actually, okay? Overall, when you build a bigger circuit out of these gates. Another interesting thing is that, you know, existing quantum computer, as you can see, has that has a limited number of qubits also, right? And hopefully these things will be better in the near future. So you can say there are multi-metric constraints now. On the one side, you have the limitation of the number of qubits. Another side, you have to optimize some of these functions on the gate functions also, right? Now, you can think in this case, the quantum computing is different from the classical computing. You can say in the classical computing usually have the 0 and 1. But in the quantum computing, you can say your qubit can be somewhere in the state of 0, 1. That's also a possibility, right? Okay. Now, you all know about the superposition thing. You can think in this case, a qubit can either be in the state of 0 and 1. And with this coefficient alpha and beta that is being illustrated here, and this alpha square plus beta square will represent the probability that either of your qubit is in the state of 0 and 1, right? When you measure it, then only you can know it, right? That is being illustrated in the superposition principle. So that is, if you think in this case, is different from a classical domain to the quantum domain, right? Another thing that is of useful is the entanglement. And you can say that if the two qubits are there, A and B, and if the entanglement properties helps in that way, suppose you measure one of the qubits, then it is also possible to get the information about the other one, right? Because they are entangled with each other. So now, as I discussed with you, the challenges, and here we will look into the fault tolerant set of computing. That's what we, and in between, I will also give you illustrative example of one application for the NISQ also. But most of this thing we'll talk about as optimizing this set of gate called the Clifford plus T gates, where we are talking about the fault tolerant quantum computing domain, right? So the underlying idea is that if you see, these are set of gates available to you, and you can assume in this case that a set of gate, let's say in this case a T gate, is slightly more costly to implement than the other gates, right? So your underlying idea is that whenever you are mapping your circuits, actually from algorithms to circuits, you're trying to minimize this number of T gates in your circuit because they have the more cost than the other one. As a rough example, you can consider that a T gate is equivalent to the 100 C naught gates in terms of a cost, actually, right? So this is one illustrative example. As I discussed with you, there is a Toffoli gate. We discussed it's a reversible gate. And this is how that if you try to map that Toffoli gate into this Clifford plus T gate set, that's how it will look like, right? You will realize this function into the sub functions, which is the quantum gates in nature. They are the Clifford plus T gate, and this is how it will look like. So you can say there are a set of T gates that are available. And as you try to build circuits from these Toffoli gates, the T cost or the T count of these functions are keep on increasing. So our objective is to minimize the number of T counts. You can say that's a simple way to assume right now, right? So now let's move from that domain to the arithmetic domain now, right? We look into some of the basic ideas. Now we are moving to the arithmetic domain. So if you look into any textbook and if you look into how a full adder works, then this is three inputs of a full adder, and these are the two outputs of a full adder, right? So these are X, Y, Z. It is adding three of these, you can say, a classical bits right now for the time being, and the C and S are the outputs of this. Is the C is the carry out and S is the sum. So if you try to take a Carnot map and try to create some Boolean equations out of it, you will see the equations will look like something like this. The sum is equal to this one and the C out is equal to this one, right? Now, we all know that, and especially those people who are working in the classical domain can find a lot of information in the classical literature textbook, right? Now, the interesting problem that I want to emphasize is that why it is difficult for us to convert a simple classical algorithm, classical circuit, or the classical way that is being taught in the classical textbook to equivalent of a quantum circuit. Why it is difficult, right? So this equation, I think, is understandable to everybody. Now let's move forward. So this is one illustrative example that if you want to create a quantum adder or reversible adder in this case, this is how can you design it. As I told you, you will have a one-to-one mapping. So of course you will have another you can say another ancilla lines here that is being added. And this is the place you are getting your like a sum, your carry, this is a sum and this is your carry output, right? So now if you see, you have to add one ancilla line in order to make a 1-bit reversible adder that could have application in the quantum computing domain, right? Now, what we can think, okay, this is fine, we design it. Now, why don't I look into any logic design textbook in the classical literature and start building adders out of it? That's how you can look into this case. For example, this is an illustrative idea of a classical ripple carry adder, right? So in this, if you look into the classical ripple carry adder, here people talk about rippling the carry. So you can consider it's more like a bit slice type of thing. So you are adding this this particular 1 bit, then it is going to the next one, it is going to the next one, it is going to the next one, right? This is how a classical ripple carry adder that you read in the classical textbook has been taught, right? But what is the issue do you see here? The issue that we see here is that because of this one ancilla line that you are adding here in this case, if you design this way that is being in the classical textbook, this quantum adder or the reversible adder in this case, the issue is that for every times you have this zero, that is ancilla line, ancilla line, ancilla line, ancilla line, right? So in other words, if I have a n-bit quantum adder, I am adding every time ancilla lines. That is, in other words, that is increasing the number of qubits in my circuit, right? And of course, right now we have the limitation on the number of qubits, right? It might be possible that who knows, in the future that these types of adders could be useful also. So I'm not denying that actually. Okay, you will see that realistically sometimes this adder could be useful also actually. But if you have the limitation on the number of qubits, then of course you can say that it's not working in that sense, right? So now this is, as I told you, you will have this overhead. And now the interesting idea is that can I think in a different angle so that I don't have to pay this overhead in terms of ancilla lines, right? Okay. So that's what we will discuss today. Actually, we'll look into some of these arithmetic circuits that are being explored in those directions and optimizing the gate counts also. We have been working in this area for a long time, actually. So we have published several interesting papers in these directions. And if you can look into some of these papers, which we're discussing in today's lecture slides. And if you need more details, you can also contact me actually. Okay, there are several papers we have published on these topics actually. So let's try to understand an example of first illustrative example of a ripple carry adder. Now we are looking into alternative ways of defining this adder such that the ancilla lines are being minimized. Okay, so this is you can say a register. You can consider it as a quantum register in this case, and it has this C0 is the carry input, and our objective is to add two of this, you can say this qubit register, in which one of them, the data that is being A is being stored. Another one is another register in which the B is being stored, right? So what we are trying to do in this case, if you ask me, we want to add this A plus B. Very simple, right? We want to do A plus B, right? And from this A plus B, which each one of them you can say is stored in an n-bit qubit register, we want to add these things, right? Such that we don't have the overhead. So in between, there is a design methodology, which like any researcher who is exploring these types of things has to work on. And it might be possible that some of the attendees who are listening to the talk today can come out with their own methods in the future. But let's say there's a design methodology, and your objective goal is to convert these registers in such a way that this carry input is still there. And sorry, actually, there is also like a C in here that is being stored in this one. Okay. So this is this C in is still here, and this register A is still available to you like this. But you see this register B has been transformed to your output of the sum, right? So if you see in this case, whenever you will have a sum, this sum is being transformed to this register B, okay? Or B is being transformed to some output, right? So this is the goal, and the underlying idea is that if you look into this way, there is minimum ancilla lines that are being used here, okay? That you will see now, okay? So over a period of time, actually, this is a very nice paper. I will advise you who are looking into arithmetic circuits to look into this fundamental, very nice paper that is being written by Kokoro, Draper, Quittin, and Moulton. It's a very nice work, actually. So here you can think in this case, each of this, I also try to show you this Boolean equation so that you can see it. So this is more like the CC0 or the Toffoli gate. This is the Feynman or the C0 gate, right? So this is that one. So you can create a block called majority block, and you can put like this C0, right? This is C0, this is another C0, and this is Toffoli gate, right? Or the CC0 gate. So you create majority function. Then from this, you can create an unmajority function, and this is again unmajority. And the underlying idea is that, as described in this paper that I showed you in the reference, is that if you cascade a majority block with an unmajority block, so you see this is my carry input. This is my one of the two input that I need to add. It will go through this majority. It will perform some functions, and it will. This is the C out that I will get. I will put it to unmajority block, and what will happen? This CI will still be a CI, right? I got it back. AI, I again got it back. While this B has been transformed to my some bit of the full adder that we want to do, right? So you can consider this is the fundamental building block, and this building block can be used to design a bigger adder circuit, right? And that is being illustrated again in this example here. So you see that this is my carry input. In this case, we have assumed it to be 0, but it can be a Cin also. And then you're putting some sort of these majority blocks, majority blocks, majority blocks. And then after that, it is being done. And then you're doing that, right? And another interesting thing is that why we are also doing it, because you can say it is going like this, the computation going like this. It is more like a V-shaped structure, right? Is that we want to make sure that we don't have too many garbage outputs being produced. We want to clean up the outputs, right? So that they are again to the same state or the useful state that you can use it again. So that is another thing that is happening here. Okay, so you can see this is a simple example of the ripple carry adder. Now it will give you some idea, at least from this talk today, that how the things has changed from the classical computing. We are simply cascading the blocks. And here in the quantum domain, you have designed a different types of approach to design the same adder, because you want to minimize the ancilla lines, right? So you can say most of the Q is being transformed. If you can assume, let's say this is the ancillary lines, then only probably we need the ancillary line in the last stage. Okay, that is what it is. Okay, so ancillas can be minimized, right? Now, in 2013, we looked into this architecture actually, and we thought actually if there's a way to design this architecture better in terms of optimization. So we at this time, instead of using the conventional CC0 gate, we look into two other gates. One of them is the Paris gate. It has these types of equations. Okay, it has we label this structure like this. Another is the logic function we proposed. This is another logic function we proposed. You can see the details in the paper, and the underlying idea, it can perform some other functions, A, B bar, XOR C, because so it gives some other properties in this case, because now you can realize a function such as A, B bar, right? Which is very useful sometimes actually. Okay. So we saw this one, and of course the gate count of this and this is almost similar. And if you see, this is the reverse of these each other. Okay. So that is another interesting idea. So we used these types of blocks. And then we came out with an optimized version of this one. This is one illustrative example being illustrated here. And you can say, again, here we are not talking about the carry in. So there is no carry in, because sometimes you don't need a carry in. You just need to perform A plus B, right? You don't need a A plus B plus C incoming, right? So this is one block. We tried to optimize these things, and you can see this more details in this paper actually, right? So now we all know that, okay, how to design an adder. Okay, now let's move forward. How can I design a quantum subtractor? Okay, so another interesting idea is that, let's say the adder is already designed. So the function of this one is that here we want to have this subtraction on this particular as this B. B has been transformed to this subtraction, this B minus A. So suppose the adder is designed, okay, and then you can see B minus A is equal to, you can write a subtraction operation like B minus A is equal to complement of B and plus A, and then you take the whole complement, right? So more details you can see in this paper. Here we have discussed several different methodologies of designing subtractor. So you should look into this paper. Here we talked about also different ways. For example, you can perform subtraction operation also as A plus B complement plus 1 by using the 2's complement method actually. Okay. So this paper will, if you look, it will provide you several different methods of subtraction. But let's focus on this one right now. So you can see that this B, you put a NOT gate. NOT gate is this B bar. So you're putting a NOT operation on any of this one. Then you're using this addition operation that this is addition adder circuit that we have designed, as we discussed previously. Now, once these output are available, then you can say that you have to take the whole complement, right? So this is being realized, and then you're putting the complement on the top, and this is the one that you're putting the complement on the top, right? So by using these things, you are able to realize a subtraction operation. Okay. So now we can move forward, and you can also design a circuit which is based on the control circuitry, can perform both addition and subtraction, right? In this case, we also have a control bit, and if the control bit is high, then we are performing, let's say, subtraction operation. If the control bit is low, then it is performing the addition operation. So now sometimes you can think in this case, you may need a circuit that is performing both addition and subtraction, the same circuit, but just changing the control bit. So this is one illustrative example that is being shown here. I think there is some chat. I don't know if there's a question for me or what actually.
Someone was just asking if your slides will be available, which they will be.
Yes, we can send the slides. Okay, thanks. Okay, so should I continue? Okay. So, okay, so you can see that this is being done, right? Okay. I hope that you are all with me till here. Okay, so we can create a subtraction circuit like that. Okay, additional subtraction circuitry like that. Okay, here is my mouse. Okay, so here. Okay, so similarly, this is called conditional adder, and you will see that this conditional adder is widely used in several applications in quantum computing. What is a conditional adder? The conditional adder is that you, based on the condition, you are adding or performing no addition. In other words, if the control bit is low, then it is just performing b equal to b. This means the input is just passed to the output. If the control is high, then you are performing the b plus a. In other words, you are performing the addition based on the control bit. So it's called control adder, sorry, conditional adder, okay, or control adder, you can also say. This is one illustrative circuit of that one. We are based on the control bit. Either this control bit is low, then this S0 will just get B0. S1 will just get B1. S2 will just get B2. In other words, it will work as a pass through. No computation, just pass through. If the control is high, then it will compute, and then only it will perform the addition. So that's called conditional adder, right? Okay, so that is, I hope that's clear also. Now we looked into this one. So now we explored this problem and we looked into, okay, this is great. Can we also look into some of the optimization of the faster adders? And if you look into these previous adders, like we discussed, most of them, like these types of adder, they are the ripple types of adder, which have, you can say order n adders, because they will take, they will have almost the depth depends on the number of the qubits that you're adding. They are the linear depth type of adder. You can say order n actually. Okay, so can we design fasters? Okay, so people, you all know from your classical literature, people can design logarithmic adders also, right? And one types of adder operation which is very much popular is the carry lookup adder, right? It is where you maybe, so let's try to look into some of these formulations. Okay, and these two papers that I discussed with you, we published a paper recently on 2020, and this is another one where we discussed two. And here I will show you both approaches. One is we consider it for the fault tolerant quantum computing domain. Another one we thought it could be useful for the NISQ machines also. So we'll discuss about that one also. Okay. So before that, I want to tell you a few interesting things, which you will be useful for almost all of you. So whenever you are designing a quantum circuit, remember that it might be possible that you may have sometimes this garbage, okay, this garbage bit. And this garbage bit is that, it is the some bit which is not performing any useful operation, and you want to get rid of it. Okay, so how can I get rid of it? So the interesting idea is that if you take a circuit, let's say if you take any circuit R, and as long as it is reversible, then if you take its transpose, that is R in, you can say, and then, so what will happen, suppose, let's say I'm just calling it as an A, and it is a reverse operation, so you will get it back again. So this is the reversible, you can say invert of this circuit. So this R, this is the R inverse, right? So that is being illustrated in this case. Suppose you have the garbage, then you can put like a C0 gate here, and that will give you this A plus B here. Then this add, I can add this add transpose, right? The add inverse circuit, which is the complement of this circuit, right? The exact opposite function it is performing. What will happen because of that? You will see that whatever the bits that is being here, it will be, let's say here it is whatever 0 or whatever here, it will get transposed. There is a small, you can say, a typo here. So it will get transformed to whatever ancilla lines you have. And this, you can get this output and all those things, right? So this is something we need to remember, that suppose you want to, and this is called Bennett's garbage disposal method. It's a well-known method. And we have discussed this detail also in our paper, actually, if you want to look into that. This is very useful if you want to dispose the garbage, you can say, bits and recycle them. Okay, so this is one interesting approach. You can put this inverse of this circuit, and it will take care of that one. Okay. So now, as I discussed with you, challenges that we have, as we discussed, we are to first, let's talk about the fault tolerant one. And this is the set of gate set we all discussed previously. It is a Clifford plus T gate set. And as I told you, the underlying idea is that this T gate specifically is 100 times approximately more costly than the C naught gate. So our objective is to minimize this gate. Okay. So let's try to understand few terminology. The T count, you will see this terminology T count, and this talk a lot. The T count is the total number of T and this T transpose T gate in the circuit, right? Then there's a T depth. Okay. T depth we are talking is the number of T gate layers in this circuit. Okay. Now, qubit cost we are defining as the total number of qubits that you require in your design. So our objective is a multi-metric constraint. Sometimes you want to optimize T count, sometimes you want to optimize T depth, sometimes you want to optimize this qubit cost, right? So depending on your optimization goals, right? So this, as I discussed with you, this is one of the example of the Toffoli gate you have seen in the previous slide, and this is an equivalent this Clifford plus T gate implementation of this one, right? You can see this one, right? So, but you see here, what is the issue? The issue here in this case, if you realize this function, this A, B, C, and let's say if I want to perform an AND operation of this one, right? So how can I perform an AND operation? You can say this is performing A, B, C, and this is A, B, and it is A dot B XOR C, right? These are the inputs and these are the output. All of you can see that, right? Now, if I want to realize this as an AND gate or AND function, I can make this C as 0. So if I make this C as 0, then this will be A dot B XOR 0, that is equal to AB, right? So in other words, if I put this and make this as 0 here, a constant ancilla line, then this particular output will be transformed to an equivalent of an AND function. That's great. But what is the issue here right now? The issue here right now that this number, let's count the number of T gates in this. This is 1, 2, 3, 4, 5, 6, 7. So you need 7 of these T gates to realize a Toffoli gate, right? Even I want to perform an AND function right now, as I discussed with you, I will still need 7 of this one, right? As I discussed, because you are using the same circuit. So a very nice approach has been proposed in this paper. I advise all of you to look into this by Craig Jidney. So he looked into some of these approaches, and he thought, actually, he proposed in this paper that whenever you want to perform like an AND function that we discussed, you can perform an optimized version of this Toffoli gate. You don't have to realize the whole Toffoli gate. You can look into the optimized version. Okay. So this is the underlying idea. You are performing X, Y, and this A is an ancillary line that is initialized to this particular state. And if you do that, then you can realize X, Y, and X dot Y. That is the AND function that I showed in the previous slide. And now this has total of 4 Toffoli gates now. So 4 T gates now, because 1, 2, 3, and 4. So instead of 7, now you're needing only 4. So you optimize the number of T gates. And again, this is not our proposal. This is the proposal by Craig Jidney. Okay. Okay. So that is very interesting approach. He used this one. Now, another thing that is being actually, this is by Cody Jones. Sorry, this is by Cody Jones and Craig Jidney. They have proposed some of this work actually. Okay, so you can look into this one. So another interesting thing you can see in this case that in this paper by Craig Jidney, you will see that there is also the inverse of this gate. Inverse, as I discussed with you, your objective is to create like this R, and then you want to create this R inverse, right? So because you want to make sure that you recycle and get it back, right? This in this case, this is X, this is Y, this is X dot Y. You're passing to this inverse function and you are getting this X and Y again, okay? And so in this case, you can say this is the control Z gate has been used for this purpose. And here the interesting idea is that this reverse operation is not using any T gate. So in this case, the T count of this one is equal to 0. So very interesting approach where the T count is equal to 0. But if you use the simple approach of using Toffoli gate, then you can see that it is a very costly approach, but here it is T count equal to 0, right? That is for the reverse operation, right? Okay. So very interesting. So these two things are available to us. So now let's look into these things. So we can design a carry look addition. So all of you, this carry look addition, you can look into your textbooks. classical textbook, it is type of an addition which has a logarithmic depth. Okay, so n is the number of, you can say, qubits or a number of bits, and it will perform the addition in logarithmic time. It requires some functions, for example, this propagate, generate, and all those things. And finally, these are some equations. This is, you can look into our paper, or you can also look into the classical textbook on carry-look addition. Okay. So our objective was that to use some of these fundamental gates that I showed to you and look into the optimization in terms of this T count for when designing these adders. Okay. And we proposed few designs and optimize in terms of T gate. Our objective is to minimize the number of qubits, and overall depth we want to have this log n actually. Okay, so that is our objective. And we propose two types of adder approach. This carry look adders, one of them is called the in place, and I will tell you what is meant by in place. Another is the out of place. The difference between those two is that here you can say if the input A, B, 0 and 0, so this is the ancillary lines. Here if you see the B, one of the inputs has been transformed to your sum output, so that's why it is called in place. In the other case, you can say this is the ancillary lines. The input are still coming to the outputs as such, but one of the ancillary lines has been transformed to the sum output. So that's why these types of adder are called out of place. Okay, and this is called in place. That's a difference between those two. Okay. So there are two different types of adders we designed. Our objective was that our out of place and in place, two different set. One of them is with low T count, low T depth. Another is the number of qubit was optimized. So we looked into, as I told you, it's a multi-metric problem. You cannot get everything. So you have to compromise on one and optimize the design further. Okay. So we looked into two different approaches. Okay. Similarly for in place and qubit and the T count actually. Okay. And this is the background of QCLA. You can see in the textbook. So I'm not going into that much detail. But what I want to emphasize to you, if you look into this paper, actually, this paper has been again by Draper and Kutin and all those folks has proposed this in 2004. Very nice, interesting work on carry-look addition. So what I want to emphasize to you is that if you look into some of these adders, actually, you can see that some of these lines are the costly Toffoli gates here. Okay. Some of these are costly Toffoli gates and several places, not one, several places, and other functions are also possible. Similarly, if you see, they are trying to realize an AND function here, they're trying to realize an AND function and all those things here, right? So when we looked into this one, actually, this is one of the master's work of my student. Actually, it was his master thesis. So I gave him this architecture. I said, you know what, why don't we look into some of these things and try to see if we can find some templates, and those templates can be replaced and see that by an optimized version, so that we can have the whole circuit either with reduced number of qubits or reduced number of T counts. So we identify some of these places. We do some of the shifting of these circuits from here such that the functionality is still same. So we look into some of this functional verification, all those to make sure that we're getting same function, but we can move some of these blocks from one location to the other gates, for example. Okay, so that is one thing. So what we did is that, as I discussed with you, these types of blocks are available from one of the papers. We try to see that, and we try to see if we can identify the places. So we identify as this is the algorithm. The algorithm is of out of place QCLA. So we looked into some of these places. I told you these are the places that are being showed in the red. We are able to substitute the optimized blocks without affecting the functionality of the circuit actually. Okay, so all this is so, and some of these places is, you can say, Toffoli gates and all those things. This is the Toffoli gate implementation where you cannot optimize it, because there at those places you really need a function exactly as a Toffoli gate. But some places you don't need at all a Toffoli gate. You are fine with either with this particular block or either you are fine with this one. And you can say if you take the whole Toffoli, then it is 7. But if you use this one, it has 0 cost, 0 T count, and this has only 4 T count, right? So the underlying idea is that to not use Toffoli as much as possible, but find this block, the computation and the uncomputation block, right, as much as possible in the circuit. So we did that, and this is some, you can see, read on this paper, but I want to emphasize to you, these are some of the places you can see. These are the colors that we are showing to you. We are able to replace some of these blocks. Again, these places you can see here. This is an illustrative example. I'm not going to details, but so, and this is how your complete out of place QCLA looks like. And then we did this comparison with the existing literature from this works. So you can say if this existing literature are there, then we are able to have the total number of T count has been reduced significantly, that you can see, okay, because we are able to use this optimized version, right? Similarly, this is some of the optimization in terms of T depth. You can say that this T depth is also reduced in our case, actually, because we are using the version which has less number of this T gates and T plus gates, right? So that's why the T depth is also reduced in our case. Then this is another example of the in-place QCLA. Similarly, you can look into this more details in that paper. But again, I think you got the idea that what we are doing here actually, right? So we are trying to identify the blocks which we can replace it by the optimized versions actually, okay? And okay, so this is again in place. As I showed to you, these are some of the equations, and we compared with some of the existing works. And as I showed to you, we have substantial reduction in the T count, or also in terms of the qubits and all those things, right? Okay. Now, this is a T depth comparison. So now this is what we thought is interesting for the fault tolerant quantum computing, right? When we are talking about this Clifford plus T optimization, right? Now, another interesting thing we thought actually is sometime in these NISQ machines, there can be sources of errors, right? Okay, and you can see that sources of errors can be in different types. For example, gate errors, state preparation, measurement errors, and measurement operation is also one of the operations. If you see the NISQ domain, can cause sometimes the error in your qubit, right? So our interesting approach was that what can we do different if you want to transform? Can I use the same adder, or should I need to do different if I want to take this adder and apply on the NISQ quantum computing? And what we think we need to do something different here, and I will tell you the reason why. So again, this is all of you are familiar with that. So what we did in this case is this is your logical AND block, right? This is the logical AND block. You can say this has again the T count of 4, but you see, but if you look into the previous blocks, the uncomputation operation was like this. It has some measurement operation. If you really want to realize as a NISQ machine, again, remember that I'm talking if you want to realize this as a set of NISQ gates, then it requires some measurement operation here actually, okay? So that could introduce some errors. So our objective was that how can we make sure that it doesn't introduce, we avoid this measurement, right? We avoid this measurement if we want to map this gate on the NISQ domain, okay? So what we thought actually the better way is that you take this gate and take the reverse of this gate. So whatever the gates you compute, and you just start instead of, so in other words, the computation can go this way, but you can also go the computation from this to this side, right? That is the reverse side. So this is the block, and this we call it the uncomputation block, right? This is exactly, if you call it R, then this is equivalent to R inverse without any performing measurement. But what is the drawback here? The drawback is that the cost of this will be slightly high there, because there are people who are trying to optimize T count. So they were using some operation here. It will take more T gates, that's okay, but we are not performing any measurement right now, okay? This is just simple reverse of that operation. So you just realize uncomputation block or uncomputation of the AND block by using this approach, right? So now we use this one, and now we can use these types of designs for the NISQ carry look adder, okay? So that is what we emphasize, that on those places where you need to perform uncomputation, you don't use that particular measurement type, you use the reverse one, as I discussed with you, the reverse one that I showed in the previous slide. And our objective is that we want to avoid measurement in between. We want to perform the measurement as at the end actually, so that we don't introduce the errors in between actually. Okay, so that was one of the underlying idea. And so this is the one, as I told you, this is specifically applicable for the NISQ machines actually. Okay, and this is, you can say, our design actually here. Okay, so it's still better, but it is, as I told you, it will be slightly more costly than the other approach. But here our objective is that it will be less error prone in that way. Okay, so these are two of the approaches. So you can look into this paper more details. Okay, now we discussed already addition operations in different angles. Let's move to a more complex operation called the multiplication, right? So you can see that multiplication is a widely used domain, and if you want to multiply two numbers, then how can we do that actually, right? In quantum computing domain. So if you see, I will show you two different approaches. One of them is this is, suppose you want to multiply A times B, and this is one of the algorithms, add and rotate. If you want to go into details, you will find this one. But the underlying idea is that you will check this bit each. Suppose you're multiplying A with B, we'll check the A bit. If it is 1, then if it is A is 1, then you will add P is equal to P plus B, and then you rotate it. Then you rotate. So you show this, you got P plus P, then you're performing the rotation operation. So what is happening, because the rotation operation, this will come to here, and this will come to here. So you're rotating it just, right? So you're just checking here in this case, if A's particular bit is 1, and based on that you perform plus B, and then you rotate, and like that it will keep on going, right? This is the type of multiplication operation, right? So you're performing addition and rotation. That's, remember that we are not performing shifting and all those things, just rotation, add and rotate. Okay, so we looked into this algorithm and we specifically use it. We specifically use the rotation operation, because in the rotation operation, as I will show to you, we can do it without any ancillary lines. It is a very, very low cost operation. I will show to you the rotation circuit. That is one reason why we use rotation instead of other operation. If you look into the classical textbooks, you can say, people will say, use the shift operation, left shift, right shift. We don't want to do that because we think it will increase the cost in terms of ancillary lines and all those things. We just want to do rotation because it will not in any ancillary lines. I will show to you. So this is one illustrative example. I don't want to go in details, but suppose you want to perform some numbers, this is how you can perform multiplication, right? So here, as I discussed with you, depending on what do you see here, what we are seeing is there, if the bit is 1, then you only perform addition. If you don't perform, if there is, this bit is not 1, then you don't have to perform addition, right? So that's why we need a control adder. And this is one illustrative example of control adder operation, right? In this case, depending on the control bit, either you perform the addition or you don't perform the addition. Second operation that I discussed with the rotate operation. And this is one illustrative example I want to show to you. Very interesting. So here, suppose these are set of qubits and you want to rotate those qubits. So this is the, let's say, the 7th qubit, and you want to bring it to the 0th place, right? So very interestingly, you can do this possible without any ancillary lines and very complex circuitry. This is the steps. For example, you can say this is a step. Then during the first stage, you change some of this. Okay, then this second stage, and finally you will see this isn't happen like that. Okay, so this is the whole algorithm you can find in this paper. In this case, you can perform the rotate right of any reversible circuit actually. Okay, using swap gates only. So this is one example as I discussed to you. So in this approach, you can say this is P0 and P7. In the end, you can say the P0 has come here. You can see that, right? Okay. So that is one illustrative example. You can perform the rotation operation very easily. Okay. Now these rotation circuitries are available. You can use this add no operations and rotation operation, add no operation, rotation operation, and through this block, you can design a multiplier. Okay. Again, we can design a multiplier such that there are minimum number of ancillary lines and all those things, right? Because our objective is to save the number of qubits. So very simple way of designing a multiplier actually. Okay. Then in 2019, we revisited this problem because we thought actually even in this, there were slightly, some ancillary lines were still needed in this case. So we revisited this problem. And here, this is one of my work done by one of my PhD student. He's right now assistant professor, Edgar Manoj Corias. So we looked into this problem, and our objective was that, can we do some more optimization in T counts and all those things, such that so our objective is about T count and ancillary lines, as I discussed with you. So we looked into 3-step algorithm, and the underlying idea is very simple here, because you can say that this is AND operation, then this is 2 power 1, this is 2 power I, like that. So this is how you can perform an addition algorithm, right? So so the underlying idea is that depending on the control circuitry, you can perform either the addition or no addition. So this is the control adder, and this is a set of Toffoli arrays. Okay, so we arrange it like that. So the underlying idea is that if you arrange this Toffoli arrays, this is a set of Toffoli arrays. Okay, this is a set of Toffoli arrays. This is a control addition. If you arrange it such that this is a Toffoli array, this is a control addition, and all those things, you can able to perform this multiplication of 2 quantum numbers actually. So this is B0, this is the numbers you are multiplying, this is another one, this is set of ancillary lines, and you pass it first to Toffoli array, that control addition, like that. And the underlying idea is that these bits are transformed here to your product output, that a multiplication is the ancillary line, and this is my original operand. So if we do this case, you can say that we are able to have the better number of, you can say, total number of this qubit reduction also, right? Total number of qubits and all those things, for example. And the ancillary lines is also reduced. So previously you can say that we have, this is the second one that I discussed with you, our approach. But here you can say we are able to reduce the T count by using this method. So you can see that, right? The number of T count has been reduced because we are using much more simplified building blocks in this case. Okay. Now, once these things are available, can we perform division also, right? So then we looked into the same problem, and this is, you see this work is available on IEEE Transition on Emerging Topics in Computing in 2019. So this is a non-restoring division algorithm. What I want to emphasize, look into the algorithms and try to identify the components. So if you look into these algorithms, what do you need? You need if the Qn is equal to 0, you perform addition, else you perform subtraction, y equal to y plus b, y equal to y minus b. If r is less than 0, you perform addition. So what do you understand? We need the building blocks to realize these algorithms, some adders, subtractors, and all those things. But our objective is to make sure that you don't pay too much penalty in terms of number of qubits and all those things, right? So we try to use these blocks. One of the blocks, as I told you, is the subtraction block, and you can easily realize this one. This is a subtraction block by further addition. This is the control addition or subtraction. You can perform either addition or subtraction by using this control bit and by using this addition circuitry I discussed with you already previously. Then you look into these blocks, and if you look into the whole paper, what our objective was that the input are registers that are labeled B and Q. Register Q will have the quotient, R will have the remainder. So this R will have the remainder here. B is another one, right? And Q will have the quotient here. So if you look into this particular algorithm, we try to understand these algorithms and very intelligently put the blocks such that you are able to perform whole division operation with just subtraction and control addition subtraction. This is a subtraction block, control addition subtraction block, like that. And then you will be able to realize the complete division circuit. So it has 3 steps. First of all is that you need to apply subtraction circuit to put some of the register bits, right? Then you perform step 2, you perform control addition, and this will be repeated n-1 time because the algorithms require it. You can see more details here. And then you keep on adding these times n-1 block. The step 2 is continued. And then the final block is the step 3, where you again need, is you don't perform control addition subtraction, you just perform control addition, this particular block actually, right? So by using this method, so what I was able to convey to you, you can say that by using some of these simple arithmetic blocks, you can realize the complex algorithms also intelligently, okay? So, and this is the one we emphasize. And here our objective was that you can say we are able to have very much optimized in terms of T gates. And I will be very happy to say and discuss that this division algorithm that we have proposed, it has been widely used by so many people. It has been widely used in so many literature and all those things, because that is one of the, you can say, one of the first work in those areas where people have really optimized it in a very nice way, rather than just using the is a conventional layman approach. We really looked into the algorithms. Me and my student, we brainstormed, and we came out with this idea such that the circuit is very much simplified. Okay, so it takes a lot of efforts, but finally you can say that is a fruit, and a lot of people are using these algorithms. I have seen many companies papers coming out. They are also using some of these algorithms that we proposed. Okay, now once these circuits are available, what can we do with that actually? Okay, so people are doing some of this work. People are using some of this work in finance portfolio, or quantum chemistry, or some sort of other complex nuclear physics algorithm experimentation. A lot of people are using these arithmetic circuits, and I can say that you will see many of these places our work has been referenced, because we have proposed some of these fundamental arithmetic circuits, right? So here I will illustrate you one simple example. This is an example of the image processing. Here our objective is the linear interpolation, right? So this is linear interpolation. Suppose you have this known pixel, this is a known pixel, and you can interpolate this pixel. This is a linear one. You can also go for the bilinear interpolation, where you have this known pixel here, known pixel here, known pixel here, and from this you can find this pixel from here, x bar, y bar, right? This is called the bilinear interpolation, right? You are knowing the adjacent pixels here. So in order to, let's say, if you want to perform the scaling of an image, scaling of an image means that that you reduce an image by an integer value, say example n. Okay, you can look into more details in one of our paper here. And so suppose you want to scale down an image, so it will require some circuits. But let me illustrate you one example. This is one of the examples of the color, pixel color. This is mostly like gray white type of images. So this is one of the examples that is being shown that if you use bilinear interpolation and in a quantum computing domain, and you want to produce the new color value from the existing color value, then these are set of operations that you need to perform. That is what I want to emphasize to you. So you can say this is 2 power n, this is a subtraction here, this is a multiplication here, this is again a multiplication, this is addition, this is again a multiplication, this is subtraction, addition. So we can see that this is again a division, or you can say 2 power 2. So you can again shift it if you need. You don't need a division, you can just shift it. So what I want to emphasize to you is, look at this problem as an arithmetic circuit problem and see that you need a set of complex operations to realize this image processing algorithm. That's what we did. So we tried to create some of these blocks. As I told you, quantum addition circuit, quantum subtraction circuit, this is a multiplication circuit I showed to you. And from this block, this is one illustrative example that how can you use a scaling down circuit in a quantum computing, right? And you can see these building blocks are available to you. And from these building blocks, we can create a new, like a bilinear interpolation circuit. And we have explored some other problems also, but this is just to illustrate you. And if you look into the literature, you will see some applications of this quantum arithmetic circuit in several other domains. Okay, and this is the numbers, so let's not worry about them. So in conclusion, what I illustrated you today is that the design of several of these arithmetic circuits, and these arithmetic circuits could be useful in several of the quantum algorithms, from cryptanalysis to quantum chemistry to quantum image processing, finance portfolio. You will see, you search the literature, you will see several places where these arithmetic circuits are being utilized. Okay. Finally, so I conclude the talk here. I want to emphasize to you that at Springer Nature Computer Science, that we have launched a new section on quantum computing and emerging technologies. And I serve as a section editor of that one. So through this, those researchers who are doing the research in this domain, it just launched in September 2020. So it's a new section, and we are accepting the manuscript. So if you have topics in this domain, then please go ahead and submit it. There are also some special issues that are we are running right now. If you have some paper, you can also submit to the special issues, or you can just submit to the this section. This section will be remain always open, so you can submit it anytime. This section, especially quantum computing and emerging technologies. Okay, this is a great one because it is a journal by Springer Nature, and so I encourage all of you to please have a look. And finally, there are some PhD positions in my research group, and these are fully funded research positions from fall 2021 and spring 2022. If you are interested, if some of the graduate, undergraduate, or graduate students are exploring those positions, please send me an email. So with that, I'd like to conclude my talk, and thank you, everyone.
Thank you. If anybody has any questions, feel free to ask. You can either do it aloud or type them into the chat. We'll read them. To start things off, yeah, I mean, I had a question. It seems like, as you've emphasized, a key element in your work is like identifying these building blocks from which you can build more complicated circuits. And, while the building blocks may be simple, the final circuits are often quite involved. And I'm just curious, what your process is in terms of designing them and presenting. Do you often work out their logic? Is it on the whiteboard with pen and paper with graphical design tools?
Right. Very good question, actually. So what I want to emphasize to you is that this is a very good question. So sometimes you think in this case that if you look into the classical or the existing synthesis approaches, you can use some of these optimization algorithms. For example, you can use, I'm telling you a very simple example. You can use greedy based approaches, right? Or dynamic optimization. You can use game theory. You can use several different optimization approaches, right? Okay. Because there it is more generic approaches. But here the interesting idea is that these are specific circuit. We can say it's an application specific circuit, because multiplication is a multiplication, right? You see what I'm saying? It is always going to multiply two numbers, right? Division is a division. If you want to perform a square root, it is going to remain square root, right? So here, if you look into that problem in a specific problem, try to identify the solution for that specific problem, then the chances of you coming out with a better solution is significantly higher, rather than you developing a tool, a generic tool that is developing arithmetic circuits. Does it make sense, right? Because there it is a generic approach. But here, what I'm emphasizing to you, that square root is going to always perform square root. Multiplication is going to always perform multiplication. So can we go into the algorithms and try to identify the places where the optimization can be done, right? So that is the first approach. Second approach is that the difference is that when you look into from classical to quantum domain, you have to start thinking. In this case, you have to start unrolling these algorithms, because in quantum computing you don't have this feedback issues, right? So because you want to avoid the feedback, so you want to unroll this algorithm iteratively, right? So I think in this case, if the algorithm is running n time, in a simple classical way, I can create a for loop and an algorithm can run time, right? Here I'm unrolling that algorithm such that it is working n times of same thing, right? Then try to see if I'm going from this step one to step two, if there is a common connection that I can take care, such that one common connection can be utilized in another common connection, so that they are killing each other, such that I'm able to save the resource count. So these are some of the approaches. These are some of the approaches that you can utilize for the optimization, right? Then it might be possible that you can come out with one solution that has very, very good qubit cost, but its delay is very, very high, right? So then you think in this case, what I can use such that I can compromise the number of qubits. I can, let's say one interesting idea. Let's say if you add 2 qubits, but you reduce your depth by a factor of, let's say, n by 2. Maybe it's worth it, right? Because you're just adding 2 qubits, but your depth is reducing by almost half. So your computation can work in a less time. And if you see in this case, the shorter depth circuit are very useful for NISQ machines, because the lesser the depth, the computation can work more reliably. So you think in this case, it is sometimes our approach, it is like we do brainstorming on these things, we take the problem, then sometimes we leave the problem as such, then we come back to the problem and see if there's a way to solve this problem. And then of course, as I told you, the good thing is that there is also tons of literature on the existing classical arithmetic circuits. You can read those things, but one thing I want to emphasize, they cannot be directly converted to quantum arithmetic because the goals are completely different. Because if you look into the classical domain, people are trying to optimize area, power, and speed. There are different numbers there. Here you're opting on top, and here your objective is to optimize qubits, T counts. So there's complete domain. But of course, you can look into the existing literature still and think, how can I transform that algorithm in an efficient way in a quantum domain? So it's a very interesting problem. And as I told you, we have done some work, but still there's a lot of work to be done. For example, you won't find too much circuit that can perform logarithmic of the number, anti-logarithmic of the numbers. For example, scientific computation, trigonometric function. So a lot can be done actually, right? Similarly, if you think in this case, people have also talked about some work on the floating point arithmetic, right? That is, floating point is a very costly operation. How can you realize an efficient circuit of quantum computing that can perform floating point operation in a very, very efficient way? And this could be very useful for high performance computing applications, right? If you just take simple, like a simple floating point arithmetic and just try to convert it, it will be significantly high overhead conversion. So that cannot work. What is the new thing you can do here? A lot of work can be done.
Thanks. We have a question in the chat. Marty asks, do you think it might be possible to use superposition to eliminate repetitions of the same circuit?
I think that will be very interesting approach, to be honest with you, because if you ask some of these things, we are still thinking in some of the circuits in a reversible way. But when you look into the superposition way, then you are also taking into quantum effect into picture. So I think that could be another interesting direction to explore, to minimize some of these things, or probably come out with some another way of doing the computation of the arithmetic circuit. So that could be another interesting direction. So I think that's a great way of thinking. Yeah, are the circuit applied to any machine learning algorithms? That's an interesting thing actually. So I think that could be another interesting direction. I'm not aware of, say, example. Yeah, people are looking into quantum machine learning and all those things. You might have seen already some talks in your things. But as you can see that some of these operations in the machine learning require arithmetic. So I'm sure that this could be also used there. Signal processing, another example. Yeah.
May I ask directly without the chat? I wonder, and some of the previous questions may be leading to that too, there is a situations where people have dedicated circuits, okay, in the classical. And maybe there is room to do a hybrid where you have a quantum circuit dedicated for certain purpose, which is coming again and again and again, and combine it with specific problem-specific software that will activate or call this, like Raspberry Pi, you know, quantum Raspberry Pi, or Arduino, quantum Arduino.
Right.
So this, like in the spirit of the other questions, saving repetitions. And in fact, you could have a dedicated circuit that will allow you for future designs of quantum circuits. It's like Gödel saying a program that is writing a program in terms of software, but maybe we can translate it to the quantum's hardware domain.
No, I think that is a good point actually, because see, if you look into some of this work, when people talk about hybrid classical and quantum type of computing, right? I don't know actually. See, this could be interesting actually. I have not explored this, especially this arithmetic type of domain in that type, but that could be interesting approach, because can some of these complex things which is difficult to realize even in arithmetic domain in quantum computing can be mapped to classical, and still we take the leverage of that one, right? Yeah, I think that could be very interesting research direction for people to pursue actually. Yeah.
Thank you.
We have another question from the chat. Anant asks, what could be done to reduce the complex quantum circuits for arithmetic operations for their actual hardware implementation? And on a related note, I mean, one thing I was thinking about is like, if it were up to you, if you were running IBM, say, and, what would you focus on in terms of, gates and operations?
Correct.
Make them really efficient. Like, would it be T gates or what?
No, actually, so if you ask me, that's a good question. So see, if you ask me, let's say if you want me to run on say example, let's say 2 or 3 different types of adder, right? Okay. Now, which of these adder work more reliably on the NISQ machines? We don't know. Does it make sense, right? Okay, because whether it will be one which has the least depth, that's what our intuition says, because you can finish the operation in a shorter time. Then what types of impact will play if you map it on the number of qubits, right? So these are some of the interesting problem actually from the NISQ side. But if you look into the fault tolerant domain, then of course the goal is completely changes, right? Because then you're talking about this gate count optimization, number of qubits and all those things. If you ask me, if you look into the NISQ, I think our objective will be, rather than gate count optimization, I think our objective should be to see if we can finish the computation more reliably, right? Okay, so that I think will change the domain from, if you look into any circuit that you're mapping on the NISQ, your objective should be to make it work with less number of errors. But in the other side, if you look into the fault tolerant domain, then of course the optimization is, can I run it faster? Can I run it like with less number of gates and all those things, right? So that I think the optimization goal will change. So what could be done to reduce the complex quantum circuit for the actual hardware implementation? So what is mean by the actual hardware implementation? So I think I got the first part of the question, but I did not understand for the actual hardware implementation.
Sir, let us take the example of spintronics-based realization. In case of spintronics-based realization, there is a qubit decoherence. So in that case, we need to have minimum number of operations to avoid the qubit decoherence, so that the operation is possible within the coherence time. If the circuit is complex, there may be possibility that the operation would not be possible in the desired coherence time. So in that case, we need to have as minimum circuit as possible for the realization.
Correct.
So yeah, my question was related to that thing.
Yes, so that will be interesting actually. So I agree with you. For in that case, let's say when we really talk about the actual hardware implementation, then we may have to see that. That's a very good point. Like for example, let's say when you're talking about spintronics gate, right? How many spintronics gates will you encounter when you really map these circuits onto to the actual hardware, right? Okay. So then actually, to my understanding, you may have one more constraint coming out from the actual hardware realization, right? Okay.
Yes,
that
sir.
is another interesting problem, because then you can put another constraint saying that here I'm also talking about the actual hardware realization and trying to see that whether, how can I make sure that maybe a hybrid type of approach will be better, right? Say example, let's say maybe a circuit which is performing a ripple carry to some extent, but after some time, it is, as soon as you started seeing the error, you can start putting some part of the computation as carry lookup approach, right? So that I think could be very interesting approach to explore if you really consider the hardware errors. Probably you can create some sort of like some MATLAB models or something like that, or run it in the actual like this Qiskit or whatever, or and try to see that how does your circuit behaves in those scenarios.
Thank you, sir.
We have another question in the chat from Martin, if about error correction. So he's asking, can there be perfect error correction? For example, can you eliminate errors completely with the probability of error being 0?
So that I think, you know, that is more like the objective of this this error correction codes, that they are trying to put this error correcting code, assuming that you can perform the computation in more reliable sense, right? So so I'm not sure if the objective there is to completely eliminate the error, or is to make sure that we are able to eliminate error to some extent, that at least the computation is start working reliable to some sense, right? So I think that could be the case there. Okay, so next question is on arithmetics. Yeah, so for example, if you look into, there is a one paper that has discussed, actually not one paper, one or two papers that has discussed some sort of arithmetics functions for sine, cosine, trigonometric functions. But in my opinion, actually, they are available, but the more optimization can be done on those operations there. But there is one paper actually, at least to my if you search specifically, it is called quantum arithmetic circuit for elementary function or something like that. So there is one paper, if you search, you will find some of this function that has been realized by the people, but not a lot. So there is a lot of opportunities in this area.
I kind of want to ask in a way the reverse of Marty's last question. If you allow for unreliability, or like a kind of unreliable arithmetic circuit, do you think you could get like higher efficiency? Like if you're willing to sacrifice, you know, being a couple bits off when you add or subtract or multiply?
Yeah, that is another interesting approach. I agree with you. Actually, that is another interesting approach, because if you really introduce the errors, then so I think, as I told you, these are all the open areas where people can put their thoughts on, and but right now this could be possible, right? For example, let's say if you really need to calculate all the bits, maybe not, right? Okay, there could be some application where you don't have to actually. Okay, so those, but on those cases you may have to identify some applications where it could be useful, right? Because you are okay, let's say if you are having some errors, but there may be some fields. For example, one is example is image processing, right? Where, let's say if I have pixel and all those pixels are slightly blurred, do I really care? Maybe not, right?
I'd like to open up the floor if anyone wants to unmute right now, kind of give you the space to ask a question. If there's anyone.
Yeah, errors are part of reality in the sense that noise will never be completely eliminated. So we have to live with error.
Mm-hmm. Yeah, I think, see, if you ask me, that I can see, because that's how the classical world operates, right? Actually, see, I'm not sure, because right now it is, people are talking about small qubit where there's so much error. So it will be interesting to see that how the field evaluates in the next 20-30 years, right? But to my understanding, see, if as the field evolve, I'm sure that people will be able to come out with some ways to mitigate error to some level, maybe not to complete level, but to some level, so that at least your computation can get executed with some with, you can say, with greater degree of accuracy. That is what I will say to you.
Tushar in the chat asks, as quantum circuits are vulnerable to noise nowadays, do you think it will be costly to implement them?
Actually, see, the thing is that actually, that's a good question. So if you see the costly, then another, as I told you, for example, let's say if you take an adder, right? Okay, because we talk about this adder circuits and all those things. Now, uh, one interesting problem that could be, let's say, if you want to add two 4-bit numbers, right? Simple, and let's say you run on any NISQ machines, and that NISQ machine is performing addition for you. Now, one interesting thing could be, let's say, if I add slightly more gates, then does it reduces my error? Or if I change the topology of the adder circuit, does it saves my error? So the answer could be uh, could be could be yes in some sense, because let's say if you want to design a NISQ adder which has short depth, then one of the possible approaches could be like you don't use ripple carry adder, you use carry look adder because it has shorter depth, right? Of course, when you have the carry look adder, then you are performing the circuit on a shorter depth, but its area overhead will be substantially more. So it will be more costly to implement. So I think to some extent, because you want to perform more and more operation in parallel in the NISQ domain, so I think it is going to be more costly in that way.
I had a question about like challenges of this. Besides the technical and mathematical challenges that you mentioned earlier in the presentation, do you foresee any challenges towards quantum computing, like that quantum computing might face in becoming a more widespread form of computing, maybe more like some kind of social issues or like institutional issues?
That is a very interesting question. But see, I'm not sure. But one thing that I think is of importance in that case is that if you think in this case, let's take one simple example, right? So, for example, right now people are talking about this post-quantum cryptographic algorithms, right? Okay, and so the underlying idea is that these algorithms cannot be broken down by the quantum computers, right? Okay, that's why people are looking into those areas, right? And but what if in the future people can come out with some algorithms which can be possibly run on quantum computers, and even those algorithms which are people are calling it right now quantum resistance can be broken down, right? Who knows, it might be possible that after some time people can think there are so many geniuses in this world, right? So somebody can come out with some new algorithms that is completely quantum in nature, but even can break this quantum resistant cryptographic algorithms. Then you can think in this case the people security and privacy and all those things will be really in a big trouble, right? So those could be some interesting issues that I think could evolve in the future actually, which I don't think will be very near term, but hope it might be possible that it just depend on one algorithm, right? If somebody does create a new quantum algorithms, which can even break this quantum resistant algorithms. So it will be, let's see. Yeah.
In this vein, do you believe that the blockchain and the new crypto technology is sort of defense through such development of breaking the RSA and the other things that gave us, let's call it now, temporary or current security in the finance world?
Yeah, that's a good way. I don't know if many people have looked into this quantum blockchain types of approaches, but it will be interesting to see how these things evolve. Uh, to be honest with you, I don't have I cannot tell you completely on that aspect, because it's still a research topic to explore. But I think that like some alternative ways for security could be explored that can, as you said, it could provide it like a permanent solution rather than like the temporary solutions, right? Yeah, I don't know what is that permanent solution, to be honest with you, but I think it will be interesting to explore those things.
I had a question. I was sort of intrigued by an interview you gave that I saw on YouTube, where you were discussing getting interested in like Vedic mathematics, something which might offer like a new perspective on a seemingly finished subject like arithmetic, which everyone thinks they know how to do. And I myself am interested in how different eras with different forms of communication and record keeping encourage different kinds of thinking. The kind of math that a culture based around oral transmission of knowledge is going to be different from the kind of math that grows up, when writing is around. In particular, like the role of mental math will be different. So I was curious, I don't know that very much about Vedic mathematics. I'm just curious, what it is, what makes it distinctive, and if there's any Vedic tricks that might lend themselves to a quantum implementation.
No, that's a very good question, actually. So what I think, that, see, if you ask me, my interest of this arithmetic circuits developed because when I was an undergraduate student, like long time back, I started implementing some of these algorithms, you can say, like Vedic mathematics, or you can say the ways of implementing this computation faster in a mental arithmetic manner as a hardware. Okay. So what I think could be interesting is for anyone, like say, let's say if somebody is an undergrad right now or looking into arithmetics, it is always sometimes possible that look into the past literatures and what people might have done it already, and try to see, maybe if you ask me, it might be possible that some of those knowledges were very valuable, but it might be possible that the technology was not there at the time to implement some of these ideas, right? Okay, so that's why probably some of those things did not pick up during those stages. Now let's say it might be possible that nowadays we may have already those, like for example, one idea people were talking about, this superposition based say ways of implementing arithmetic functions, right? Now it might be possible that some of these algorithms which are not widely talked, I'm not saying it is Vedic, but I'm just saying it could be any one of them, which is available, let's say, from our past ancient sciences, and maybe read more on those things and try to bring some of these things to the current literature. So it is always possible. For example, when I was reading some of this textbook on Vedic mathematics, I will tell you one interesting idea that came to my mind actually at the time was how to perform the square and the cube of any number in a very efficient way. Okay, because because the idea, it came to my mind because I was reading Vedic mathematics in those days actually, and I found out that that if you want to realize any hardware of that one, and if you just use Vedic mathematics, because if you, one simple example I will tell you. So in one of the algorithms, Vedic mathematics says that if you want to perform a square of two numbers, you can perform a plus b whole square. So that is equal to a square plus 2ab plus b square, right? It's a very simple way. Now think in this case, this 2ab is nothing. You have to calculate a times b and then you shift that one operation. So that is won't give you too much benefit if you're just considering one bit, but let's consider whole of them as a 4-bit or 8-bit blocks. Then it will give you significant saving, because then 2ab means that you will just compute one of the big 8 to 8 times block and you will shift it one times and it will do the job for you. So that will result in significant area and power savings in classical computing. So what I'm trying to tell you is that it might be possible that similar ideas could be clicked for application in the quantum domain also. Okay, or not only quantum domain, or in some other domains also where the arithmetic circuits are being utilized. So I always encourage people to look into this arithmetic textbook, which has people have done already in the past in the literature, and you may get some new ideas from them also.
Maybe I'll ask another question. Just curious, what words of advice you would have for someone starting out today in the field of quantum computing, besides looking at, interesting work from the past and so forth.
Right. So, uh, so what I will advise actually to the student, actually, especially, it is, I will give the generic advice actually. Okay. Those, let's say, let's consider this advice for the people who are just starting as an undergrad student, right? Okay. Because so what I will advise usually is that for those students is that right now, uh, get involved as an with some people who, let's say, find a good mentor. That's the first thing. Find a good mentor who can help you to enter into the area, who can help you to teach some of the fundamentals, take some courses on those topics, and then get involved as a researcher, as an undergraduate student. You know what, I will tell you honestly, fortunately I get involved in the research as a second year undergraduate student actually. Okay. And then by the time I complete my undergraduation, already have at least 4 to 5 research paper published by the time. And I will give the credit not only to to my to my efforts, but I will also give credit to the good mentors that have come across my way, who has really helped me to evolve over a period of time. Okay. So the good mentors plays a big role in your career actually. Okay. Finding good mentors, when I say the good mentors who are ready to give time to you, right? For example, so find those people who are willing to find time for you, and you will surely find some of the people, and take some independent studies and all those things. I always have a lot of undergraduates working with me, and I really give them good amount of time. And because you can say many of these undergraduate becomes a future graduate students, and they do really well over a period of time. So what I will suggest to the people is that identify a good mentor who can guide you, read research papers, and then you can say, then you can not only enter into the quantum computing, you can enter into any research area that you like to pursue.
Thanks.
I have a question about
Oh, Anna, it's hard to hear you.
steps for your work. Do you hope that in your project you work with some kind of project and like implementing some sort of optimized algorithm somewhere? You might. Oh no. Okay. Yeah, I got an internet. My back. Okay, probably not.
Yeah, so if I understood your question from your text, you're asking about the next steps for the project, right? So next of the project could be like, say example, take any application such as quantum chemistry, or say example, quantum image processing, or let's say nuclear science or material science, and apply and take those algorithms and take this. In other words, the objective could be a set of libraries of arithmetic functions can be provided, which can become input to this quantum algorithm, so that when you really realize this hardware of this quantum algorithms for applications such as finance or any applications, those algorithms can run efficiently on the quantum computer. So that is the next step.
We have time for some more questions. If anybody
Okay, there is one.
concerns?
Since superposition is so powerful, but it's actually using very simple probability concepts. It's powerful because it's really physical, it's quantum mechanics, basics. The question would be, is there a way to extend in this direction using more probability stochastic concepts and even going wide, like using something called fuzzy logic circuit?
Yeah, very
where I have ensemble of
right.
several circuits, and they're having errors, they're having all kinds of things, but eventually the average of their results will be lovely.
Right. No, that's a good point actually. So if you look into that, see, I've not looked into too much from the fuzzy logic aspect, but if you think in this case, there are work on multi-valued logic actually, where they're trying to use this multi-valued arithmetics and all those things to see that to see that the algorithms can be optimized with less number of qubits and all those things. So but what you said about fuzzy logics could be interesting, but I'm aware of the works on the multi-valued logic. So there is some works that has people have explored on multi-valued logic, or let's say ternary arithmetic or quaternary arithmetics and all those things. But from that fuzzy logic aspect, I am not sure if many people have explored or touched that area, but it could be interesting to explore.
So you started out like in a classical computing context before you got into quantum circuitry. Is that true? And if
Yes,
so, what,
yes, actually, that is 100% true. Yeah.
yeah. So like, what was the moment for you when you decided this is the new direction that I have to go in?
Right. So I will tell you one thing. So fortunately, fortunately, when I was doing my PhD was in mostly in, you can say, on this emerging technologies actually. Okay. And my PhD was mostly focused on designing this reversible computing circuits and all those things. And at the time, you can say the quantum computing is always there, but it was just like a lot of momentum was started momentum gaining up on those things. So I thought actually maybe we should try to focus. So we were trying to optimize this reversible computing circuits for other emerging technologies, right? For example, there are other emerging technologies for the conventional classical areas, and our objective is to look for the low power and all those things. And I still do it actually. We looked into some of this domain for low power computing for security applications actually in classical domains. We have a lot of students working on that. But then I thought actually, because this reversibility is finding also a lot of application in the quantum computing domain, then and quantum computing has a huge impact, then why not we try to see that and optimize these circuits now for the quantum computing domain. So fortunately it worked for me in that way, and that's how it started for me actually, specifically. Yeah. But for the audience or anybody, if say example, those who are here and were not able to say example, you can anytime drop me an email on all those things. I will be happy to send some of the papers, or we can brainstorm further on some of these topics. I will be happy to discuss on those things.
Well, thank you. Yeah, I mean, if there's no more questions, we can wrap up. Thank you so much, Dr. Thapliyal. This was very enjoyable. Hope you had a good time too.
Thank you, everyone. Actually, I really enjoyed it, and I think it was. I really like the questions and the brainstorming and all those things. I think it opens a lot of. If you ask me if there are many audience who are looking into new topics, it also opens some opportunities for them to think about the new topics because the conversation. So it was great. And thank you, everyone. And I really enjoyed it. And thank you to the organizers, to everybody. Actually, it was great. Thank you. Yeah.
Thanks for coming, everybody.
Thank you, everyone. Take care. Bye.
Thank you.
Bye.